right. Hello and welcome to the third lecture in this design module. Today we are going to conclude the design of beams. And this is something that we've been talking about over the past couple of weeks. And the process is as follows. To finish the design of a beam, you need to do mainly three separate checks. Design the beam for flexure, for bending, design for shear, and check the deflection is not exceeding the allowable limit. Last week, we dealt with the flexure design, or bending design. And in order to do that, there is one major question you need to ask yourself. Is this beam laterally restrained or unrestrained? If it's laterally restrained, it's pretty straightforward. If it's unrestrained, it takes a little bit more time to figure out the capacity. And in essence, what you need to do, you need to reduce the capacity to account for the possibility of lateral torsion buckling. We covered this part. Today, we're going to talk about shear design and how to check for deflection. And as a matter of fact, let's just start with the deflection. So, checking deflection is under a different limit state than the safety or bending and shear. Bending and shear, this is ultimate limit state. You check these capacities to prevent collapse and catastrophic failure. Deflection is for serviceability, to make sure that the ceiling is not deforming too much, to make sure that the beam at the edge is not crushing the window, to make sure that when there is a lot of people on the floor above us, the doors are not going to jam and they're going to still work properly. All these things are for the building to function properly. So we need to pay attention for deformation. So let's start with deformation. I want to talk about two main things. What are the forces that cause deformation? Or what are the different factors of deformation? And what is the allowable limit? And comparing the two, make sure that the actual deformation doesn't exceed the limit, then this design is good. If your design has way more deflection than the allowable limit, then you need to do something about it. This is not acceptable design. So who tells us what is the limit for deflection? What is the maximum allowable limit? The design code. So to avoid having this uncertainty, what would be the actual allowable limit, the code will suggest a value. Having said that, sometimes your client will specify what is the maximum allowable deflection they're comfortable with. And I can give you an example that I personally faced in a project I did. Some designers, architects, companies will ask for the windows to be like a curtain wall. Like the entire facade of the structure is windows. So you hire someone to fabricate these windows. The fabricator of the windows will communicate with you, with the structural engineer, that the maximum deflection their window can take is that much. So now, even though the code could say you're okay with more deformations, you need to communicate with your client. You need to check vibrations, so something like what happened now doesn't scare the occupants. All right, so these are the two things. I want to talk about source of deflection and what is the allowable limit. There are three main types of deflection. Deflection due to the permanent load or dead load. This is typically under the self-weight of the structure. The permanent finishes, you can consider this as permanent load. So you can estimate the self-weight and the dead load and calculate deflection due to dead load. There are two kinds of dead load. There is the short term and long term. Short term, when you finish pouring the concrete, immediately that weight is dead load. There are factors that depend on time, like creep and shrinkage. These are factors you probably heard about in your study of concrete material or structural materials. With time, the properties of the element could change and could result in what's called long-term deflection. Long-term deflection is usually because of creep and other long-term forces. Some design codes, they differentiate between the two, but for the sake of our lecture here, let's say this is dead load or deflection due to permanent loads or permanent dead load deflection. The second type, you probably guessed it, it's life load deflection. So the deflection under our own weight. This deflection is not permanent. When we walk into the room, the floor will deflect. When we leave the room, if the deflection is within the elastic limit of the floor, it will rebound. So it's very important check. When the occupants are using the building, what is the deflection due to live load? And you differentiate that from deflection of dead load. The third type is very interesting type of deflection. It's induced deflection. It's in deflection that you actually intentionally introduce to the structure. It's very common in steel structure. It's called camber. Camber, or an induced upward deflection. So when you manufacture the steel beam, you actually manufactured deflected upward like that, cambered upward, and you specify to the fabricator, to the manufacturer, how much is the camber you want. You want a camber from 5 millimeter, 10 millimeter? You have a question?
Yes, I didn't install a camber.
That's a great question. Why would you want to build the beam deflected upward like this and ship it to site and install it with this upward deflection? What would that, so what would be the necessity to create that upward?
After loading, after putting the load, it will be balanced and then...
To balance the dead load deflection, right? The dead load deflection is downward. So you can balance the dead load deflection by manufacturing the beam cambered upward with the amount of the dead load deflection. So it's important to be able to calculate the dead load deflection, and you may want to specify a camber on this structural element. And those are the three different types of deflection. How do we calculate them? Do you have a question?
Yes, in the camber, if we did the camber, does it affect the load distribution?
Load distribution. What do you mean by load distribution?
I mean, the load is applied.
Yeah.
And the load is going to go from the beam, from the slab to the beams to the columns. I mean, if the beam is got the camber, so the distribution would be different, right?
That's a great question. That's a great question. I would say if the beam has a roller on one end, it doesn't matter. The deflection will straighten up, and that side will is free to move. You might run into issues if this is a statically indeterminate beam, a continuous beam. I would say if the camber is minimal, it shouldn't change the distribution of the load. If this was like an arch girder, if this was like a beam that has a significant curvature, absolutely, that will make difference in the reactions. Because the arch want to open up at the bottom, so that would affect your reactions. That's a good question. So before I move on to the limitation, the code limitation, how do you calculate each type of deflection? Do you have a question?
Do we always use the camber, or
that's a very good
the
question.
shape of the beam, or do we use it according to our support?
What do you think? Do you think you always have to create a camber in a beam, or you might want to use a straight beam. What do you think? If you're designing a building, would you order it from the fabricator cambered, or you tell them, you know what, it's fine, just send it straight? What would you do?
يعني على حسب الكامبر ده.
حسب اللود مش كده؟
I-
If it's not, there is not
حسب
much
اللود اللي
deflection,
عندي.
we will push it straight. But if there is a huge deflection that we need to be balanced, so we will then يعني نعمل camber.
Do you have anything to kind of add? So what would you do?
تمام زي ما عمر قال.
What did he say?
He said if there's a lot of dead load, we will use the camber. If it's okay, we will use the original.
I would personally tie it to the dead load deflection. If the dead load deflection is very significant, I could start introducing a camber. That's a very good question. So now my question, the question I just asked, how do you calculate each type of these three deflections? How do you calculate the deflection due to the dead load? From this formula. No, you don't have to get this from the code. This is a structural analysis formula. As a matter of fact, just a couple weeks ago, we just introduced the deflection formulas. If you go back, you will find that this formula over here is the maximum deflection for a simply supported beam with a distributed load at top. So if this had a point load, you will have to use a different formula. Does that make sense? So this formula only works for this beam. Distributed load, simply supported. If this was like fixed, it will have less deflection. The deflection would be less than that. And you get it from formulas as well. All right, so what is the W? What would be the weight you use in this formula to get the deflection? The dead load. Dead load will give you put the dead load in the formula, you get dead load deflection. You put the live load in the formula, you get live load deflection. Okay, how do you calculate the camber?
Is equal to the dead load. Right?
Pretty much, yes, and you specify it. Like the fabricator, the manufacturer will ask you how much camber do you want. You could say 0, I don't want any camber, and then the deflection, the downward, will be the dead plus live. Does that make sense? Yeah, no question?
ممكن تثبت على كده الكامبر ممكن يكون يفضل كده.
Well, the camber is preset. It comes to the site cambered. When you apply load on it, it kind of deflects downward, so
What
they
type?
cancel each other.
What type of load?
What is the first load that will be applied on the beam?
ده
Dead load.
يعني its own load.
Its own weight, and then anything you put on top of it will keep on deflecting downwards.
طب تقدر تشرح فوق كالفليت بس عن اللايف لود ما هو كان لايف لود بلس الديد لود.
Live load plus the dead load?
يس اللي هو اللود بيتحط على البيم بلس اللود بتاعها او الويت بتاعها.
So this has to do with what is the allowable deflection.
Yes.
We will go through the Eurocode and the Egyptian code and see what each code allow us to do. Does that make sense? All right, so moving on, now that we know how to calculate dead load deflection, live load deflection, and what is the function of the camber, let's figure out what the Eurocode suggests we do. So this is the exact wording for the Eurocode. I got this from the steel section, and you will find something very interesting. Eurocode will suggest that the actual limitation be defined by the annex for each country. For each member of the European Union, they can have some say or some control what is the allowable deflection. So here is what I want you to know about the suggestion for the UK version. The Eurocode for UK suggests that you limit the live load deflection only. It does not ask us to check or limit the deflection due to dead load. So you still need to do something about it. It needs to be a reasonable design. You don't expect your beam under its own weight to be like sagging all the way like this. So it's a good standard practice to either provide a camber or make sure that the deflection under the self weight is not excessive. Once you do that, you follow the limitation of the code. So the code ties the allowable deflection to the span. It's always a ratio of the span. And it tells us the allowable limit for different elements, depending on what's attached to the element. If the beam has a window attached to it, or non-structural element that could be damaged, it would say, do not allow this beam to deflect too much, otherwise it will break the non-structural element. So what do I mean by a non-structural element?
Windows.
A window. A window is not structural. Despite you might look at it in a way that is supporting the wind. When the wind hits the building, it hits the window. And the window needs to be able to support itself to transfer the load to the structure. That's the only kind of maybe structural factor or function of the window. Other than that, I'm not relying on the window to transfer the load to the foundation. So this is how you interpret these limitations. It says, for cantilevers, a cantilever is like a beam with an overhang, with like a free side. If you have a balcony, do not allow the tip, the free end of the balcony, to deflect more than the span divided by 180. So if that cantilever was like 3, you divide it by 180, that's the maximum allowable deflection due to live load only. Eurocode will check the deflection based on live load only for the UK suggestion. Beams carrying plaster or other brittle finishes. So if there is a beam and it's supporting fancy tiles or has like a window supported on it, you don't want it to deflect too much. And then the deflection would be the maximum deflection, the span of the beam divided by 360. Most common beams, if like a beam is like over here, there's nothing underneath it, the finishes above it are not very sensitive to deformation, you would use for like other beams, the span divided by 200. So I would kind of follow the recommendations. If it's a generic beam, it would be the span divided by 200, unless I tell you otherwise. I could say the maximum deflection you should check for is the span divided by 300. So then you would use the recommendation. All right? I want to talk to you about the Egyptian code. The Egyptian code has a slightly different approach. The Egyptian code will ask us to do 2 different checks. Check for live load only, similar to the Eurocode, and check live load plus dead load. And it has different limitations for each case. Yeah, go ahead.
Exam. Which code will we use?
That's a good question. I will be very clear what to use, what is the limit to use.
So we must practice on both codes.
Yes, yes. Having said that, you don't have to feel confused in the exam. I'm going to be very clear what to use and how to use it.
في الامتحان الفورمولاز اللي هنحتاجها هتبقى معانا ولا هنخش في الامتحان وندور في الكود؟
Yes, you can bring it with you.
ايه هي يعني
The formulas you need.
يعني it will be there or not?
It's an open book. So you can bring your formulas. So you might as well start now preparing the formulas you need. So it's like a practice of design. When you're at work, when you're at work doing design, you would reach to get like a structure analysis book, a design code, and go through it. Yeah, that's the formula. And I want to make sure that you can produce a safe design, a design that is good in bending, shear, deflection. Go ahead.
Wait, so we have to get the codes with us?
You don't have to get the actual book.
No,
You
I mean
can
like the
prepare
codes
your
we're
list.
gonna use.
What's that?
The codes we're going to use, for example, for deflection,
Yes.
We have to like either know it or get it with us on a piece of paper or something.
Yes. Having said that, you don't have to get the actual book. You can use the booklet on Moodle. On Moodle, you can find like a booklet with like a summary of all the main parts that you would use. So you can print that and bring it with you. You don't have to bring all your library with you on the chance that you might use. You can do that. Yeah. You can do that as well. All right? So speaking of exams, this is something that you can expect in the upcoming test. I will give you a beam with a load and ask you to design it. And I expect you to check for 3 things. Design it for bending, check shear capacity, and check the deflection. And when you're done with this, now this beam is safe design for ultimate limit state and service limited state, and then it can be part of a structure. It will be safe for people underneath it and on it, and it will deform and perform according to design. It's not deflecting excessively. Let's do an example. So first step is going to always be to calculate the load. We did that in week 1. So if you want to practice more, just cover these tables and figure out, knowing the thickness of the slab and the live load, how do you get the dead load and live load? So after you do the analysis, you will realize that the thickness of the slab is dead load. Any finishes or screed or topping, whatever permanently on top of the slab is dead load. The self weight of the beam is dead load. The only live load is the live load. So there is just like the weight of the occupants. If this was an office space or whatever the use is, you go to the code, see according to the use of the space, what is the life load. It happened to be 5 kilonewton per meter. Yeah, go ahead.
السؤال ده جالي مرة في الامتحان اللي على
Yes.
بس ما كانش مديني thickness. حلها ازاي لو
That's a great question. That's a great question. You can just like let me know about this issue and we can fix it. So what do we do from here? You need to get the dead load and live load in order to get the dead load deflection and live load deflection. So how do I get the dead load and live load deflection? From the deflection formula according to the loading type. Does that make sense? So when you look closer at the formula, you will find 4 things. The weight, dead or live. The length, where do you get the length from? From the floor. You're designing a floor that has a span of like 6 meters, so the beam is 6 meters, that's the L. How do you get E and I?
Eurocode depends on the material.
E depends on the material.
Why is the resistance of the material as well?
It's the moment of inertia.
Yes, sir.
How do you get the moment of inertia? From the design. You design the beam, and from the tables, like the commercial steel section tables, you choose a section that has a moment of inertia strong enough to resist bending, shear, and deflection. There you go. Okay, so here is the application. This example is to check it against the Eurocode suggestions, and the Eurocode checks deflection under imposed or live load only. So do you limit the 9.9 millimeter or the 10 millimeter to the allowable limit? So do you make sure that the limit is not exceeded under live load or dead load?
So we add them together.
The Egyptian code would ask you to check both, live load only and live load plus dead. Okay, so what is the allowable deflection for this beam? According to the Eurocode suggestion, it's the span divided by 360.
Yes.
So how much is the span?
Is the 9 meters.
It is 6.
Yeah, yeah.
divided by 360. So the maximum limit is 16.7 millimeters. Do not exceed 16.7 millimeters. How much is the actual deflection? Well, according to what load? According to the dead load, will deflect 10 millimeters. Live load will deflect 9.9 millimeters. So should I add both and compare it to this?
Yes.
Or compare just one or the other?
Add them both.
No, compare each one.
It depends on which code you're using.
If the Egyptian will
The Egyptian code will say check both.
يعني add both ولا
Add dead and live and compare it to the suggested value, and check live load only to the other suggested value. This is why the Egyptian code has two limits. One limit for live load only, and another limit at the same case for dead plus live.
ماشي بس لو هي لو dead plus live يعني هي مش safe كده صح؟
Yes, that's a good point. If you add dead plus live, it's more than 16. The thing is, this is the limit for live load only. For dead load plus live load, it's a different limit. So you check with the corresponding limit. Yes.
هترجع للكود.
Yeah.
Egyptian code.
Yes.
هو الأول واحدة الداد لوحدها صح؟
This column is the maximum limit for live load only.
اللي بعديها داد ولايف.
Dead plus live.
طيب هو مش أنا المفروض بطلع الداد وأتشيك على دي وبعد كده أطلع اللايف والداد وأعملهم قد بعض وأتشيك على التانية؟
No, the other way around. You get dead plus live, and you check for the right hand column.
اللي
And
هي
250.
250.
yes, that's dead plus live. The left hand column is just for live load. Just the deflection under live load. All right? So let's solve this according to the Eurocode. The Eurocode gives just like one set of limits for live load only. Does that make sense? The Eurocode is kind of like more flexible in this way. The Egyptian code is gonna like ask you to be more thorough. The Eurocode will give more flexibility since this is a serviceability issue. It's serviceability issue. At the end of the day, if you break the window, you're just gonna replace it. Hopefully, it doesn't fall and kill someone. That's another source of liability. But you think of it this way, right? What are the safety factors, or what is the liability you're attracting and your client is attracting as well? That's a very interesting thought, because you could do something and then your client takes your design, the structural drawings, and builds it, and then someone gets hurt. And then the person that got hurt will sue the owner of the building, and the owner of the building would say, like, I did not know. I hired the structural engineer to do the design for me. Go sue them. So what would you say? You would say, I followed the recommendation of the code. Go change the code. And that's kind of like the way to kind of think it through. Otherwise, if there was negligence, someone got hurt because someone neglected the dead load or something like that, this is where serious liability. So avoid being in that situation. All right. So it will make more sense when you cover the answer and just make sure you crunch the numbers and you design the beam for deflection. You can expect that part in real life for sure, and for the sake of like the assessment we're gonna have shortly. And that leaves us with one more check to be done with the design of beams. Do you have a question?
By designing the beam, you mean by so calculating the deflection in millimeters and then choosing it from the table, right? Or the value we're getting is thickness of the beam.
So that's a great question. How do you make sure that your beam is satisfactory for deflection? Yes.
The R factor deflection is less than or equal to the maximum allowed deflection limit.
Yes, so the actual deflection is less than the allowable limit. That's the goal of the deflection check. Make sure that the actual deflection of the beam.
How are we designing itself?
So we started by bending design. Yeah, go ahead.
I mean, so now we have the bending design, we have the shear force, the values then.
Yes.
We're taking the values and then selecting, the same thing we did last year, selecting from a table according to the values.
maybe أرانا section أنت تخليه إيش؟
So you chose a section. Remember here, you chose a beam that has a moment of inertia that you got from the commercial tables. Does that make sense? So you need to check that that moment of inertia, that it's not going to deflect too much. So it's a check. You check that the
Oh, so
section
I
you
already-
chose,
So I choose my section and then
you
I
chose it in bending design. Having said that, sometimes you would choose a section, it will be okay for bending, but it will deflect too much. So now you need to choose a stiffer section, a stronger section. Does that make sense? So that will be the design in that regard. If you chose an I for a section that it was too flimsy, too weak, it deforms too much, then you choose a bigger section. So that will be the deflection design,
Okay,
so to
we're
speak.
just comparing the results.
Comparing the results, that's right. And the main factor is going to be the moment of inertia of the section you use. And obviously the material. If you're checking deflection for steel, it's different if that beam was made out of concrete, because E is different, modulus of elasticity is different. All right, so let's figure out how do we design the shear capacity of the section. I want to point out something that is very interesting to know in terms of design. For steel beams, the top and bottom flanges, these are the horizontal parts in an IPE section. It's called a flange. The top flange and bottom flange. These are critical for bending, because bending stress has maximum stresses at the top and at the bottom. So we care about lateral torsion buckling and the yield strength of the section and so on and so forth. For shear, this is the shear stress distribution over the section. So I need you to know what bending does to the beam and what shear does to the beam. This is a small section of this beam. This beam is an IPE section, it has top and bottom flange, looks like an eye. And if you take a chunk of it, the bending moment is trying to bend it. The shear force is applying vertical Fy force on it, trying to shear it. That's what scissors do. Scissors can apply vertical force, it's trying to shear a bar. And this shear force introduces this stress distribution. Most of the stresses are on the web. The vertical part of the eye, this is called the web. Let's look at what the Eurocode suggests for the shear capacity. Do you have a question?
Yes, I don't understand the drawing for the stress, the stress. I don't get the drawing.
This one here?
Yes.
This is the shear distribution on that section.
Oh, so this is the shear diagram for the...
It's not the shear diagram. This is the shear force diagram on the beam.
Okay.
This is the shear stress distribution. Do you understand this diagram?
Yes.
What is this?
This one is the bending.
It's the bending stress distribution. And bending is like bending like this.
Yes.
Shear is like a vertical force parallel to this area.
Okay.
It will induce stresses maximum at the mid-height. And it looks like that. So the majority of the stresses are acting on the web. And therefore, the shear capacity of the section depends on the area of the web, the gray area, plus a little bit of a root or a little bit of excess material that connects the web to the flanges. All right? So long story short, the Eurocode suggests that the shear force, you get it from the shear force diagram. The shear force on the beam is less than the shear capacity of the beam. How much is the shear capacity of the beam? It's a very simple, straightforward question. equation. It's this equation. It's equation 6.19 in section 6 in Eurocode. This is the actual equation from the code. It says the capacity for shear under plastic design. Do you guys remember when do we use plastic design? If the cross section is class 1 or 2. Class 1 or 2, you design it for plastic design. So if you choose class 1 section, use this equation. If you look closely, this equation depends on a factor of safety at the bottom. According to the code, this factor of safety is suggested to be 1. So we know the factor at the bottom is 1. The only remaining factors is the yield stress, the maximum yield stress of steel, and the area of shear, AV. What is AV? It's the area of the gray shaded area. Does that make sense? How do you calculate it? Yeah, that's a good question. The code tells us how to calculate it. You get the entire area and you subtract 2 times the width multiplied by the thickness of the flange. And then you add the thickness of the web plus 2 times the radius of the connection between the web and the flange.
So كل الحاجات دي الكود هيكون يعني
Yes.
دي standard.
Yes, it is. It is standard equations. You should bring the code with you and you should practice going through these formulas. So don't make it the first time you're going through this formula at the test or the first time you're designing a beam. Just get a solved example and make sure that you get the final answer correct. All right? So this formula is actually much simpler than it looks. When you simplify it, it will look something like this. The shear capacity is around 0.6 or 0.577 area V, which comes from like the area of the gray shaded area, multiplied by the yield strength of steel. Now, there is a critical issue that could happen that could result in an under design or a problem in your beam. Your beam could fail in a certain case if you have bending and shear at the same section. So what does that mean? Let's say at the midpoint of this beam, how much is the bending moment at this section? Let's say this is section 1. How much is the bending moment at this section? Yes, how much is it? It's WL squared divided by 8. So it's a big number. How much is the shear force at the same section? 0. So when you have maximum bending, you have 0 shear. When you have maximum shear, how much is the corresponding bending moment? 0. So in most cases, if your beam is simply supported beam with a distributed load, the maximum shear is not going to be at the same location as maximum bending. So section 1 has maximum bending, 0 shear. Section 2 has maximum shear. You need to design it according to the equation, but it doesn't have big bending moment, almost 0 bending moment. So what if you're designing a section that has maximum shear and maximum bending? This is what this equation is about. It's called bending and shear. If a section has bending and shear. Can you think of a situation where a section has maximum bending and shear? I'm curious if you can think of a scenario where a section has maximum bending and maximum shear.
Distributed load with point load.
Yes, that's a good example. If you think of the bending moment of a simple beam with a point load P. The bending moment diagram looks like this, and the shear force diagram looks like this. So at a section like just left to the point load, you have a very high shear value and very high bending value. So what's so special about having too much bending and too much shear? You're overstressing the section. If you put too much bending, the top is approaching yield. If this is class 1, you can allow the section to develop yield on the entire section. So the section is exhausted, it's like yielding. It has no more capacity. If you add to it a lot of shear, it's not going to be able to take both. It's not going to be able to take maximum plastic moment capacity and maximum shear resistant capacity. It's too much for the section. And what the code says, if you have the shear force higher than half the plastic shear capacity from the earlier equation, you have to reduce the yield stress for the beam. So in other words, if you have too much shear, do not design the section in bending for like the full capacity, reduce it. So how much do you reduce it? Do you reduce it with? The code tells us the reduction equation. You should multiply the yield factor, reduce it by a factor smaller than 1. So it's 1 minus a factor. You get the factor from the formula. It's the plastic shear capacity we got earlier from equation 6.18 or whatever was the, from this equation, 6.18. And then you follow the formula with like the square and everything, and this will result in a ratio between the actual shear and the shear capacity from the equation. If it's less than half, if the actual shear less than the plastic capacity of shear, then use the full Fy. If the ratio is more than half, then you start reducing the yield strength accordingly. So let's take an example. This is a beam with a distributed load. Maximum shear is not at the same position as maximum bending. So I just stop, I apply in the formula and say checking bending and shear is not necessary, because maximum bending is at a different location as maximum shear. At this point load, I will have to check that. In my case, the ratio was less than 0.5, so no reduction needed. If I was stressing the shear too much, I will have to reduce the moment capacity, the flexure capacity of the beam. I could stand here all day trying to walk you through the equations. I think it will make much more sense when you cover up the answer and follow the code recommendation and see if you can get the correct answer. Does that make sense? Any questions so far? I'm almost done. I have just like one more thought to share with you. So far so good? Okay. Is this the only way you can break a beam in shear? By the section developing yield under shear stresses? There are a couple more ways. We're not going to go into too much details, but there is one more check. The web of the beam could buckle if it's too long. If the height of the beam is too big compared to the width of the flange, the width of the web, the thickness of the web, this beam is like gonna buckle under shear load. Yeah, go ahead.
هو اصلا ازاي يحصل كده واللي هو البيمز دي ستاندردز
That's actually a great question. You can build up sections. Look at the section in the middle. You can get a steel plate,
Yes, sir.
a vertical, and a steel plate horizontal, and put a steel angle in the side and make up your own section. So the code gives you the room and flexibility to design your own sections.
دي بتحصل لما بيبقى built up sections بس.
That's a great question. Most probably standard sections are not going to have this, but there are specific sections that could trigger this issue. So I need you to check it. I need you to check it. You just make sure that the height of the web divided by the thickness of the web is less than this value. The factor at the bottom is suggested to be taken as 1 as a conservative way, and the strain that you design for is from this equation. So knowing the grade of steel, you can get this number and just make sure that you don't exceed this limitation. All right? And that's the main design part. We're not past this point. We're not going to go into too much detail design-wise, but I want you to know this is not enough. You want more design?
بيقول أكتر من كده details.
Okay, yes, there is one more extra thing to pay attention to. I want you to think of this for your professional life. When you are designing a steel beam in real life, please understand that these orange pieces, they are called stiffeners, web stiffeners. These stiffeners can help you avoid the local buckling of the web. So sometimes at the supports or at specific load points, you want to introduce stiffeners to avoid the failure modes that has to do with the buckling of the web. Other than that, if you have a super high, let's say a column that is picking up multiple floors, sitting on one beam, this could be an area of very high stress concentration. The code will give you ways to design to make sure that this beam is not going to crush or the web is not going to cripple. It's not going to look like that under the concentrated load. Most probably, if you introduce stiffeners like these yellow or orange pieces, you can make the section strong enough to resist these loads. Does that make sense? All right. So that's pretty much it, what I wanted to say today. We'll take a break and we'll do some examples on what we just talked about. All right? So let's meet back here 2:15. All right, see ya.